Yeah, you'll be able to. Yeah,
No,
no problem.
I just want to
You're
ask a
welcome.
question. Thank you.
Yeah, no problem. So, last but not least, I'm going to talk about where we're headed to in the future, what we might see. So, I talked a little bit about myself. I mentioned I am a collector and I'm obsessed. Anyone who's been to the shack here knows I'm obsessed with collecting radios. Um, I like to collect radios that are of a technological importance. That's one of the interests that I have. And I started doing this way back in the 1960s. And I'm still at it. But I learned a few things. I'm fascinated with the history of communications and radios and electronics. It's something that has always fascinated me. But I think about the fact that if I'd been born 50 or 60 years earlier, I might have been part of all this stuff. But today I still look for new additions, and I've actually picked up a few recently, which I won't talk about, but they're kind of neat. Um, but let's talk about this. What makes a good receiver? Well, it really depends on your application. I mean, you might be talking about cell phones. We might be talking about communications, amateur radio, radio astronomy, satellite telemetry, other applications. They all have different needs, different requirements. So we're going to specifically focus on communications receivers and what makes a good communications receiver. Things like being able to detect the signal at the noise floor, and that's called minimum detectable signal or minimum discernible signal, MDS. The ability to withstand strong signals that are nearby in frequency and nearby physically, in other words, short distance away geographically. So that's the ability to withstand overload. Wide dynamic range, meaning that we can withstand those strong signals as well as get those MDS, that minimum discernible signal. It's very, very weak. So that's our wide dynamic range. You want to be able to hear the signal that you're interested in. So that's talking about selectivity. In other words, being able to get rid of all the other stuff around you and select just the signal that you want to listen to. And then we want to talk about the stability and tuning and resetability. So these are the goals of a good receiver. Now, believe it or not, a fellow by the name of James Lamb defined that in 1932. He was the technical editor of QST magazine back then, and I'll talk a little bit more about him in a bit. But let's talk about a little bit of history here. So, all this stuff, where did it start? Well, in 1861, this gentleman, you may recognize him, James Clerk Maxwell, he publishes a paper called On the Physical Lines of Force. And he realized that electricity and magnetism are and this is the quote, electricity and magnetism are manifestations of the same phenomena, electromagnetic field. So he was the guy that put it all together and said this is the case. Now he's resting on the shoulders of a lot of scientists that came before him, but it's considered the second great unification in physics. Now you may wonder what's the first great unification, and we can talk about Isaac Newton and terrestrial and celestial mechanics and gravity. That's the first great unification in physics. But all this work that he did is based on the work of others. Faraday, Michael Faraday, electromagnetic induction, Hans Christian Ørsted, the electromagnetic field, Henry, we know him. Henry is we know inductance is named after Henry, and Zandajewski. He suggested a connection between light, electricity, and magnetism, and so all of these, the work of all these gentlemen, all led to Maxwell publishing Maxwell's equations. So big step. I will say that there were other folks that were playing around with this stuff, and some of them were kind of interesting. This guy, William Henry Ward, he's actually awarded a patent in 1872 for a method of collecting natural electricity. Now, the only thing I can say about his patent, well, I'll say a couple of things. One is there's no basis in any kind of scientific fact, but his patent, if you go and look it up, it's got a really cool drawing. That's his collector. So it's like no scientific basis at all in what he was talking about. And the other guy you might have heard of is Loomis in 1872 patented something called wireless telegraph. Well, it wasn't really wireless. It was wireless and there was no physical connection. But there's no, the patent has no drawings or explanations or anything like that. But the guess today is that it was probably done by induction. It was not electromagnetic radiation in any stretch of the word. Neither of these had anything to do with electromagnetic waves. So, defining moment number one is the proof of Maxwell's work. So, Maxwell talked about electromagnetic waves. In 1887, Heinrich Hertz proved that he was correct. He built a laboratory apparatus that consisted of a Ruhmkorff coil, which is basically a spark coil. You can see the picture there. There's a coil, a tuned quote unquote tuned dipole, and a received dipole, which is that loop that you see there. And in 1893, his results were published, and it was called Electric Waves, being researches on the propagation of electric action with finite velocity through space. So what happened is that when he fires up his spark gap transmitter, that spark coil, he was able to produce an arc at between the gap that's in that loop. He was able to produce an arc on the other side of the laboratory. So he was trying to prove that Maxwell was correct. And of course he did. Now, this is not practical. This is a laboratory experiment. Keep that in mind. But that's really what Heinrich Hertz is known for, is this experiment. So the next guy to come along is Edward Branly, and he came up with this thing called a radioconductor. And this is a photograph of a radioconductor. You probably know it by a different name if you've ever studied early radio. But what he noticed was in a flour mill that the dust, if there was any kind of static charge, the dust would collect up and stick together. And he discovered, based on that behavior, that if he had the right combination of materials, and in this particular case, basically metal particles in a small vial, as you see right there, that when it was exposed to an electric field, it would conduct. The metals would cohere together. And so it would conduct. But it had a problem. You remove that electric field and they still cohere. But the Branly's radioconductor was able to actually detect an electric field, electromagnetic waves. So that was an important step. But if you tapped the vial, they would stop conducting. So as long as you could sit there and hit the thing with a pencil or whatever to just knock the things loose, it would stop conducting, and then it would detect a field again, and you can make it stop. Well, Lodge, a fellow by the name of Lodge, comes along. Well, he calls this thing the coherer, and he added an electric bell, just the ringer from an electric bell, that when this thing would start conducting, the bell would start moving, and it would tap the glass vial, and it would stop cohering. So by adding that ringer, he's now able to respond to Morse code. So that's a big step. So Lodge and Branly are really kind of really a big part of what's going on. But now I want to talk about a fellow by the name of Popov. Alexander Stepanovich Popov. He's a Russian. In 1894, he constructed something he called a lightning detector. And of course, it's based on what Branly and Lodge have done. But in my estimation, this is Dennis's opinion, but this is the first practical application of receiver technology. This is it. He was able to detect distant lightning storms, electrical storms, thunderstorms, based on that Branly coherer, because lightning is an electrical discharge. It creates electromagnetic waves. This thing could detect that. So he was able to have warnings of electrical storms, time way before they ever got to the location they were at. So it was kind of an interesting application. And he was an interesting guy. He didn't want to patent this. The others were playing with the same hardware, doing similar experiments, but he did not want to patent it. He wasn't interested in making money. He was probably just a guy experimenting in his garage. Well, maybe not his garage, but out in his shop in 1894. But he wasn't interested in making any money on it. But he did build an early wireless system based on this technology. Well, a name that everybody's familiar with, Tesla. and maybe not familiar with Bose, but Tesla in 1893, he actually demonstrated wireless in public. He showed a demonstration. Again, this is a laboratory experiment, but he described the methods of doing wireless communications. And in 1900, the US awarded him two US patents. Two patents. There are key US patents on wireless, but this is going to come up again. If you know this story, you'll know what he went through. These patents were awarded in 1900. What's interesting out of India is Chandra Bose. He actually demonstrated radio waves in Calcutta at the same time, about the same time that Tesla was doing these experiments as well. But they were not connected. They were independently doing this. But Bose came to London, and he met and visited with Guglielmo Marconi in 1896. Now, visiting with Marconi, Marconi got some ideas, but more on that momentarily. But this caused, between Bose and Tesla, huge flurry of interest in wireless technology. Well, in 1896, 4 years before Tesla got his U.S. patent, Marconi was awarded a patent, British patent 12039, and that's considered the initial patent for radio. But it's based mainly on the work of Tesla and Branly. These are the guys that made that happen. I want to talk about Marconi. He's a well-known figure, and there's a lot of misinformation about Mr. Marconi. I have a lot of respect for the man. He was a very brilliant, well-educated, wealthy individual, but he never invented anything. Everybody calls him the creator of radio, but he really was the one. What he did is he commercialized it. He was a businessman, and so he commercialized wireless, but not inventing anything. But he did improve on the existing ideas and the apparatus that were being used. He saw ways to improve that. So I give him credit for all of that, but he saw the business opportunity. He saw the business opportunity of wireless communications. And so this was considered the first practical application of wireless telegraphy. He improved on the coherer and the decoherer. And that's all I just say, he built really big spark coils. We're talking hundreds of kilowatts of spark and a series of wireless stations that spanned quite a bit of area. And in December of 1902, made the first transatlantic radio contact. It's interesting. A lot of folks wonder about that. If you read the story, it was predetermined what they were going to send, the message in Morse code. And so if you've ever listened to noise for a long period of time, you'll hear things that aren't really there. But he already knew what the message was going to be. So it's this figure that, well, he might have just imagined it. But the truth is that it really wasn't that impossible. In fact, today, these are extremely long waves, very low frequencies, but it's spark. At the time that this happened, there probably wasn't any low frequency propagation across the North Atlantic. But the harmonics up into the multiple megahertz, megacycles of the day, might have been what they detected. What he actually heard were the harmonics of the spark system. So regardless, he did earn the Nobel Prize in Physics in 1909, but he had to share that with Carl Braun, who came up with the idea of the crystal detector. The crystal detector replaces the coherer decoherer. And if in 1903, there was a patent awarded for something called a cat whisker detector. Some of you may be familiar with that. If you ever built a crystal set with a cat whisker, yeah, that's where it comes from. Galena crystal with a little pin contact. Well, Tesla versus Marconi, the lawsuits ensued, and the U.S. Patent Office overturns Tesla 1900 patents. Marconi is officially the creator of wireless now. He's deemed that. But Tesla pursued it. He went to the Supreme Court with his lawsuit. And in 1943, the Supreme Court revoked Marconi's claim and re-awards the patents to Tesla. But what happens? Months before this occurred, Tesla passes away. They are reinstated. And it's interesting as to why this actually took place. There's some theories on it, and I kind of ascribe to the one is that um, World War One, wireless played a big role in World War One, and by taking the patent away from Marconi, the government is protected from paying damages to Marconi for use of his patents during World War One. So they originally gave the patent to Marconi to avoid Tesla claims. So it's some interesting theories. Hard to say, but anyway, this is where it all starts. We're going to start improving receivers. I'm going to give you some ideas. These are pieces out of my collection. There's a Galena cat whisker, and you've probably seen one of those. Maybe you built a radio using one of those. The other one is interesting. It's a chemical or electrolytic detector. It actually uses an electrolyte in a little glass tube as the detector. Next, I've got some homemade crystal. There's a homemade crystal set and a loose coupler. That coil there is a loose coupler and a commercial opera crystal set. These are all common things from back in the early 1900s. And the technology really did not change much in those early days. So something new is needed. Something new is needed. This is defining moment number two. The performance of those detectors is really limited. You really require a strong signal to be able to hear the thing. Marconi used a galvanometer indicator. In other words, he didn't actually have a headphone listening to things or a speaker. He was actually watching an electromagnet that was flicking around with the signal from his detector. So that's what the galvanometer indicator is. Well, a fellow by the name of Fleming, John Ambrose Fleming, he worked with Marconi building his transmitters. But in 1904, he applied for a patent of something called an oscillation valve. Well, we otherwise know this as a vacuum tube rectifier. The oscillation valve is a vacuum tube rectifier. So patent 803,684, this becomes a game changer for receivers. This is the game changer. It's based on the Edison effect. In fact, Fleming wanted to go to work for Edison, but Edison wouldn't hire him, sadly. But it's based on the Edison effect, which says if you have an evacuated container and a hot filament and put a charge between that hot filament and a plate, the charge will flow in one direction. He added that plate into the light bulb. And so the charge would flow to the plate, but it wouldn't flow in the opposite direction. So the rectifier. So it's based on that. So Marconi's got him working for him, and now he's using the coherer with the valve and a galvanometer. So he's combined these things together. So now it's more sensitive, much more reliable, and we credit Mr. Fleming with having created the first vacuum tube. And here's a copy of his patent, and it shows this is actually applied to a receiver. You can kind of see the coil here. There's the receiving. There's an antenna and a ground. There's his rectifier, and there's the galvanometer. That's what that is right there. So measuring the current flow when the signal flows, when he picks up a signal. He was able to put them in parallel to make them more sensitive. But this is really where it starts. So next up was to make a little modification of the Fleming valve or the Fleming vacuum tube. We're going to talk about the Audion. You've heard this name, Lee DeForest. Lee DeForest creates a triode. The triode, it was a three-element triode, tri. He adds a grid between the filament and the plate in a Fleming valve. And there's an early example of an Audion. And now this works as a detector, of course, as the Fleming valve does, but it also amplifies. A small signal on the grid creates more current flow from the filament to the plate. So it actually amplifies. It also oscillates. So that's something new. We can actually generate a continuous wave with an oscillation. So he gets patent 879532 in 1908. And of course, he's in litigation with Fleming. It's just like figures. These guys are all sue happy. Um, Fleming's patent was actually declared invalid, which is interesting. I never really understood that. But for DeForest was a charlatan. I, I may be blasphemous in saying that, but this is Dennis's opinion. He was a tinkerer. He had no clue how this thing worked. He just tinkered with it until it did something. I guess he had some kind of an idea, but he came up with all these crazy explanations of, oh, it's based on ions of gas in the tube. No, that's not it. It's electrons. But anyway, there's no gas ions in a vacuum. But the guy that finally explained it was Langmuir, who worked at General Electric. And he's the one that explained how the audion worked after many, many years of DeForest not really having a clue. But I do give DeForest credit for coining the term radio. That's his claim to this genre, is coming up with that term radio. Now, history will say that he did the first public broadcast on January 12th, 1910. Keep track of that date. This is the first public broadcast, and he did a live broadcast of the Metropolitan Opera House performing Tosca in New York City, July 12th, 1910. Well, okay, we'll come back to this later because I dispute that. Anyway, the next step, okay, so he's got this audion, this vacuum tube. The next thing to come along was to build what was called a tuned RF receiver. So we now add some tuning stages to it, and the triode provides gain, and one is good. More really must be better. So more stages, more amplification. Well, to a point. So we add more stages, and what happens? It becomes unstable. It's going to be prone to oscillation. Not good. It's difficult to tune. Here's an example. This is an Atwater Kent Model 10A from about 1923. This was part of my collection years ago. I no longer own this one, but look at that thing. It's got three tuning knobs that you have to tune the signal in with. It's got a couple of controls for the filaments, so you'd set the filament brightness, and it would tend to break into oscillation and what have you. But it was an interesting piece of gear. This is from 1923. So, yeah, fun stuff back in those days. Along comes Ernst Alexanderson, and this is where I'm going to dispute Mr. DeForest. He actually developed the TRF receiver while at General Electric in 1916. And for the positive side, it had good sensitivity, multiple stages. It was sensitive. By nature, because of those tuned circuits, it was high Q. In other words, it was selective. The tubes that it used, the triodes, were inexpensive. That was a real plus. Triodes were inexpensive, but it did have its drawbacks. As I said before, it's difficult to tune all those stages. It's difficult to operate that guy. And of course, it is unstable. But regardless, many TRFs were built by many, many companies over the years. So this leads us up to defining moment number 4, the heterodyne principle. So the heterodyne principle, this guy, Reginald Fessenden, this guy, I like this guy. He proposed the heterodyne principle in 1901. Problem was, there was no technology in existence to perform it. 1901, DeForest hadn't created the audion yet. So the heterodyne principle states that if you mix F1 and F2, two frequencies, what you get is the sum and difference of those two frequencies if you mix them together. What this principle needed was the triode, and it came along 5 years later. Nevertheless, Fessenden is credited with the first voice broadcast. He's in Brant Rock, Massachusetts, and I mentioned Alexanderson. Alexanderson, the alternator, he worked at GE. He was an engineer at General Electric. The alternator created 500 watts of RF power at 75 kilocycles or 75 kilohertz. That's what the Alexanderson alternator did. On Christmas Eve in 1906, he He hooked a microphone up in the antenna lead of the Alexanderson alternator and started broadcasting. 1906, 4 years before DeForest. Now, the accounts of it say, if you read the newspaper accounts, it says it was heard in the Caribbean. No, it was heard in Jamaica, New York, 200 miles away. But still, that's an accomplishment. 200 miles in 1906, that's pretty cool. But I claim that Fessenden was the first guy to actually do a public broadcast when he did his experiments in 1906. But cool stuff. Heterodyne principle. Well, nothing's come of that yet. But along comes this guy, Edwin Armstrong. Everybody's heard of Armstrong. He's a prolific inventor. This guy is a brilliant engineer. He puts all this stuff together. In 1914, he invents the regenerative receiver. He was an undergrad at Columbia University when he invented the regenerative receiver. We still build those today. We play with them today as a plaything to build a regenerative receiver. He patented that concept, and for him that would become a windfall. So what do we got? The Audion will oscillate, but we add positive feedback to it to make it oscillate. And we add that feedback with a coil, L3 in that schematic, and that's what causes it to oscillate. And what we do is with a regenerative receiver, you get it right to the point before it oscillates. It's not quite at oscillating. And all of a sudden, the gain goes sky high and the selectivity gets very, very narrow. So you can suddenly tune in single signals, which we really couldn't do before this time. Well, in 1917, he joins the U.S. Army Signal Corps, World War I, right? He gives the government free use of his patents. What a guy. Pretty neat. So defining moment number 5, regenerative detector. Here's his patent, October 6, 1914. Positive feedback applied to an amplifier, and if you give it too much feedback, it'll oscillate. If it's just right, just not quite to the point of oscillation, you get lots of gain. What's cool about this is all of a sudden we don't have to use headphones anymore. We can now hook this thing up to a speaker, because using crystal sets and the TRFs, they typically wouldn't drive a speaker. They would drive headphones. So we had to use headphones with crystal sets, but this thing will drive a loudspeaker and you could fill a room with sound. Pretty amazing. 1914. Well, unfortunately, since it oscillates, it also transmits. That's one of the drawbacks. It's good and it's bad. Imagine living in an apartment building with 20 other people with regenerative receivers all tuned in to different stations. And what do you hear? All the heterodynes between all those receivers. Sort of like, well, if you ever operate AM, it's kind of like operating AM in ham bands. You hear all the heterodynes. But so that's the bad side of it. But this led to patent wars. Oh my gosh. RCA licensed the regenerative patent. Armstrong was working for RCA at the time. They got the patent. There were a lot of radio manufacturers using, basically licensed the patent, licensed the use. Westinghouse was one, Crosley was another, and just literally dozens of companies. But these are some of the big ones, more well-known companies that did these regenerative receivers. And here's some examples. Those are examples of two Westinghouse receivers. The Areola Senior, which is a single tube regen, and the Rada, which is a two tube regenerative receiver with an audio amplifier. And these are both out of my collection. They're kind of neat receivers, and you could add an audio amplifier to the Westinghouse, but these are all built under license from RCA. And of course, RCA made the Radiola there on the left, and Crosley. That Crosley receiver, when I received it, it was brand new, what you call new old stock. It was in the original packaging. It had never been put on the air, never been used. And it's just a beautiful example of Crosley 51. Anyway, so what comes out of all of this? In 1918, Armstrong's working at the Signal Corps lab in France. And based on Fessenden's heterodyne principle, Using an audion as a local oscillator, he uses an intermediate frequency. So he's got a mixer where he mixes the frequency to an intermediate frequency and at a lower frequency. At the lower frequency, it's easier to obtain high gain and high Q. In other words, high selectivity, and it's stable. So this is a really big step coming up with this heterodyne receiver. This is the super heterodyne. So this is defining moment number 6. It's the super heterodyne receiver. And this design holds, it's still in use today. It hasn't really changed. These are some of his early sets that are in museums. Uh, and here's the principle right here. You've got an RF amplifier, so there's an amplifier stage. There's a mixer with a local oscillator. You filter that and go through an IF, an intermediate frequency amplifier, through a demodulator to an audio amplifier. This is a very stable, very high performance system. Much more stable and reliable and higher performance than the old regenerative set. Oh, here we go again. More patent wars. So in 1928, Armstrong loses a patent to a fellow by the name of Levy. Levy had a French patent claim 2 years prior to Armstrong's work. So the U.S. Patent Office doesn't like to interfere with foreign governments and their patents. So they pulled Armstrong's patent. Bummer. But he goes on to develop FM. And we know no FM today is a very, very high performance, uh, high quality transmission technique. So he developed the concept in the 20s, and in the 30s and in the 33 and 34, so mid 30s, he's experimenting with it and testing it, and was actually awarded the patent. His first transmission was in 1937. Now, doesn't that look like an amateur radio license? W2XMN. Well, that wasn't an amateur radio license. Back in the day, the FCC issued what were called experimental licenses. They still do, but experimental license, that first letter in the suffix being an X indicates that that's an experimental license. Well, Armstrong gets into a bloody war with RCA, and RCA wins at first. Check out David Sarnoff, Empire of the Air. That'll have a lot of the story there. But if you've ever heard of that, 1954, Armstrong dies penniless. But it's Tesla all over again. The patents are awarded back to Armstrong's estate. Go figure. Well, the Super Het did have drawbacks, and the primary drawback was the cost. TRFs were still the most popular, and the Super Hets were expensive. They were more complicated, but even though they were higher performance, they were more complex. So along comes this guy, Hazeltine, in 1922. The triodes they were using were unstable, and this was due to inter-electrode capacitance. Well, he came up with something called neutralization. You may recognize that term. We use that in vacuum tube amplifiers today, RF amplifiers. We neutralize that stray capacitance, the inter-electrode capacitance, so that it's more stable and it doesn't oscillate. So that's neutralization. So he adds neutralization. He comes up with this concept to the TRF, and this becomes something called a Neutrodyne. Now you can have a TRF radio that's stable. It's still less costly than a Super Het, but it's stable. So it's a lot easier to tune, and it doesn't oscillate. So it's not transmitting like a regenerative set. So with this development of the Neutrodyne, there was formed an association called the Independent Radio Manufacturers Association, and all these companies built Neutrodyne receivers based on Hazeltine's design. And here's a good example of one. This is a Fried Eismann, and these things are beautifully built. But there you can see that there's the neutralization capacitor. It's a metal sleeve with a metal rod into it with an insulator, a dielectric. So it's like a sleeve coaxial capacitor is what it is. But that's how he neutralized these things. So moving on from there, lots and lots of companies built these things at this time. Well, along come these two guys, Browning and Drake. And this is not Drake of amateur radio, R.L. Drake, Robert L. Drake. These guys are two undergrad engineering students at Harvard. they were striving to come up with a better way to build a regenerative receiver. They wanted a better job than, and they didn't want to have to deal with RCA's patents. They wanted to get around the patent. Well, they came up with something called a regeniformer. And rather than using that capacitive feedback and the inductor that Armstrong used, it uses a loosely coupled coil to cause the feedback path. Well, this was a great idea, great design. It worked really well, but they needed somebody to make the parts for them. So they went, this is in Harvard, they're in Massachusetts. They went to a place called the National Toy Company. National Toy Company built metal toys back in the day, but they were contracted by a sales rep from the Cardwell Corporation. Cardwell made electronic components like variable condensers, what we call a variable capacitor. Variable condensers. National Toy Company made these condensers for Cardwell for their sales rep, George Hill, in Massachusetts. Well, Browning and Drake went to them and said, hey, we need variable condensers. We need regeniformers. Can you make this stuff for us? And they did. And of course, if you've been around radio for a long time and played with National, you know about the term velvet vernier that was from the National Toy Company, the velvet verniers for tuning. In 1916, the National Toy Company became the National Company, big U.S. radio manufacturer. They were able to circumvent the Armstrong RCA patents. National produced these radios as kits. The owner assembled his own radio. Aha! They just sold the parts. So National and Browning Drake were not manufacturing radios. They were just making parts. You put your own radio together. So on top of this, as an aside, National established a subsidiary country that would buy the kits and then assemble them and sell them. I think that's funny. But it wasn't encumbered by the Armstrong patent. So cool. But this sets the future course for National Radio Company, and I'll talk more about them in a bit. But yeah, National was a biggie and really had some revolutionary ideas. Browning Drake. Here's an example of a Browning Drake. Here's these are the National Radio Company regeniformers here, and their condensers. Those are all made by National. There's another one right there. And this is a really nice example of a Browning Drake receiver. Nice one. Well, National really took off with this. In 1932, General Electric was contracted by the government by what was called the CAA. That was the Civil Aviation Administration, which is now the FAA, of course. General Electric was building transmitters, but they didn't have a good receiver. But they were contracted by the government for their air-ground communication system. Well, GE goes to National and a gentleman by the name of James Millen and says, we want a high-performance receiver. Build us a high-performance shortwave receiver. Well, Millen came up with this thing called an RHM. It was a high-performance 9-tube super het, and it was called, that was the prototype. Ultimately, it was called the AGS, Aeronautical Ground Service Receiver. And it was one of the very first commercial high-performance super heterodyne receivers. Unfortunately, this is at the time of the Depression, and it put it out of the reach of a lot of hams. So they didn't have the money. Obviously, this would have been an expensive radio. Well, Millen comes up with the idea of making an inexpensive version. He removes some parts and comes up with something called the FB7, which is now a 7-tube super het, similar to the AGS design, but no RF amplifier. By the way, FB, Funbox 7. Similar to the AGS, but didn't have the RF amplifier. So here are the two receivers. The FB7 is on the left with its speaker and power supply and the plug-in coils. And on the right is an AGS. I happen to have 3 of these AGS receivers. I have an RHM, an AGS, and an AGSX. So 3 different versions of the same receiver. They only made 300 of these guys, so they're pretty rare. At about the same time, Hammarlund Corporation was coming up with this thing called a Comet, and we believe this to be the first production consumer shortwave super het receiver. The problem was it didn't work very well. I have this is one in my collection. They're extremely rare. They did not work very well. That they didn't stay in production. They were actually handmade on order by whoever you'd order one and they build it for you. And they were terrible receivers. No, I shouldn't say that. It wasn't really a turkey. It was really a landmark receiver. It wasn't really a turkey, but it didn't work. But they had to redesign it, and they came out with something called the Comet Pro, which greatly improved it. I happen to have one of those too. Well, I want to talk about defining moment number 8. And this is Mr. Lamb. I mentioned James Lamb. He publishes this article in QST. He was the technical editor. He just did a series of articles back in the 30s called "What's Wrong with Our CW Receivers?" And in 1932, he describes this single signal super het. And this is what I was talking about earlier, where he defined those requirements that make a good communications receiver. He basically defines what I call the processing chain of a super heterodyne, where the gains are balanced and so you get the optimum performance and all of that. But he also came up with an architecture for what's called double conversion, where we actually have two intermediate frequencies. Elegant simplicity in this whole setup. And this concept stands to this day. So the two James Millen and James Lamb, collaborated on many, many papers. Millen left National and went off and formed his own company, James Millen. But the HRO was really the crowning achievement back then of National Company, the HRO. And why is it called HRO? Because somebody, probably James Millen, penciled on a drawing on one of the schematics, a blueprint. He penciled on there, hell of a rush order, and the name stuck. The first one was delivered in March of 1935. It used this thing called a PW micrometer dial, or PWM dial. You can see that in the photo there in the center of the dial. Unprecedented tuning rate, very, very fine tuning, extremely resettable in frequency, something that other receivers couldn't do. This thing used plug-in coil boxes with an external power supply. He believed that the power supply created interference with the radio, so he wanted the power supply to be away from the receiver. So this made an improvement on the AGS that had all those individual plug-in coils. This takes all the individual plug-in coils and puts them in a single box, so you just plug the box in. The problem they had with the AGS is the operators would get the coils mixed up. So you'd have a coil from one band with a coil from another band and a coil from yet a third band plugged into the radio, and it wouldn't work. This product line, the HRO product line, continued until the 60s. And of course, it started with the HRO Junior, which was a low-cost version, HRO 5, HRO 7, HRO 50. Of the vacuum tube radios, the HRO 60 was the very last one that was produced in the 60s. Since then, after that, they made a solid state version, and I'll talk about that later. There was an HRO 500 and an HRO 600. But HRO is the embodiment of Lamb's ideas. They called it the cream of the crop. That right there is one of the earliest production HROs. It was probably built in the second month they were in production. And you can tell because it has this little white push button. It's actually an ivory key top on that push button. And that distinguishes the early ones, as does the PWM dial with a German silver dial. Later ones were painted, but that little push button was replaced by a little push-pull switch. You'll see that in some other pictures. So defining moment number 9, a fellow by the name of Schottky, working at Siemens. You might recognize that name if you've ever worked around Digital Logic, and in particular Schottky TTL. He develops the Tetrode and the Pentrode while he's working at Siemens. These were not widely available. They were very costly, but they really improved on the problems of some of the other early vacuum tubes. This didn't really catch on until the 30s because it really was the cost. Cost was the factor. These things were just too expensive. But World War II refined tube technology, huge improvements in performance over the triode. We added an element another grid to make a tetrode. We added two grids to make the pentode. And now we can make very high performance super het receivers, but they're still expensive, the sort of thing that only a government at war can afford. So naturally, during the war years, the government, we manufactured lots and lots of these radios for the government for the war effort. So during World War II, these things really were refined. Receiver technology is evolving. We've got better tubes, better components all the way around, better performance, better performing materials, higher density construction, and new applications. What are our new applications? VHF and UHF. We're suddenly doing that. Radar is another big application. So to give you an idea, some of you may have actually used one of these at one time as a ham, or even maybe in the military. I don't know, BC-348. That was an airborne receiver. This is a very, very well constructed super heterodyne receiver that were flown in B-17s, for instance, uh, among other things. BC-348. Of course, you've all maybe seen these guys, ARC-5s. ARC-5 were flown in many, many aircraft, but this is a super heterodyne receiver. I started out as a novice using one of these guys right here that covered 80 meters, and I ran crystal controlled with the matching transmitter from the ARC-5. So the war made a huge difference. And some of the things that came out of the war effort were this, what I call defining moment number 10 is the Collins PTO, the permeability tuned oscillator. Now, up until this time, oscillators use a variable capacitor or a variable condenser with a fixed coil. Collins came up with this idea, and they tended to be, I won't say unstable, but they drifted because of heat, changes in temperature. They had a lot of difficulties with keeping them stable. During World War II, Collins designs this PTO, and it uses a variable inductor and a fixed capacitor. The variable inductor is a solid coil wound on a form with a ferrite core that's moved in and out of the coil to change the inductance. And of course, it's a resonant circuit. It changes the frequency. These things are a lot more stable. They're much more resettable in frequency, and they're also linear, which is something that a capacitor or condenser is not. Well, in 1947, now this was used in a lot of equipment during World War II, but in commercial service or for consumer electronics, in 1947, Collins introduced something called a 75A1 receiver. This was Collins' first amateur receiver, and he used a PTO for stability. It was double conversion, so it's using Lamb's idea of the double conversion system. And of course, this is the A line, which culminated with the 75A4. And the 75A4 embraces what we call single sideband with the KWS1 transmitter. This is in 1955, by the way. That's when that was introduced. So Collins is now building sideband radios. Everybody and his brothers now making sideband stuff. Well, let me give you some other examples of Collins. This is an ARR-15. This is another receiver using a PTO. This is an airborne receiver. It's an auto-tune receiver, so you preset the channels in it, and it'll tune with a motor to that frequency. Well, I want to talk a little bit about single sideband, and especially about Collins. Sideband was just appearing in amateur radio in early 50s. Okay, man, early to late 50s. It was really just starting up. Several manufacturers are getting involved. I mentioned Collins is one. Central Electronics, obviously, was building transmitters. They built what were called splicers, which were receiving converters, so you could take your standard receiver and receive single sideband on it. Collins Radio Company, of course, was one. Drake appeared. Drake built a really neat receiver called a 1A. Bizarre looking radio. Doesn't look like a conventional communications receiver. It's an SSB only receiver, and it has this odd form factor, but it's a great performing radio. I can attest to that since I have one. It's a great performing receiver. And I think that form factor is odd because most hams, this is sold to the amateur market. Most hams had a big old clunky AM CW receiver sitting on their desk. This fit right next to it. So that it was small, compact. Well, a little on the history of sideband. Would you believe that single sideband, the first patent was applied for in 1915? AT&T, this chap, Carson, He's at AT&T Bell Laboratories. He recognizes that AM consists of a carrier and two sidebands, an upper sideband and a lower sideband. So in 1923, the patent was granted. So it took a few years, but the method and means for signaling with high frequency waves. Why is this important to AT&T? Well, they were able to take a single voice channel and put two voice signals on a single channel. So one carrier, two signals, one signal on upper sideband, one signal on lower sideband. So they conserve bandwidth. So they were the first user of single sideband. So it was used in the transatlantic radio circuits in 1927. No, these would have been the probably the cable circuits between North America and Europe. This would have been the transatlantic submarine cables, and it was used on those wired circuits until the 1930s. So they were able to get for every conductor that they got one signal on before, now they can put two. So they just doubled their capacity by just adding this technique. And we then add something called frequency division multiplexing, so we could put multiple carriers on a single circuit and have upper and lower sideband at the same time. So we get many channels on one circuit. So it's really an advantage to the phone companies, AT&T and Bell system. Well, amateurs started experimenting it within the 30s, but it really wasn't accepted until the 50s. And Central Electronics put out one of the first transmitters, which was a 10A transmitter. But this got the attention of Art Collins at Collins Radio and Curtis LeMay at the Strategic Air Command, and something called Project Big Talk, where they took a KWS-1 and a 75A4, stuck it in an airplane, and flew it around the world using single sideband on HF to communicate with that aircraft. And they found that it worked a lot better than AM. So that was a big step. Well, in 1950, Collins came up with another item for communications systems. Actually, they had been building filters for the phone industry for years, single sideband on the phone circuits. So they've been doing this work for many years. They used this in the multiplex circuits and doing the double sideband type thing. They had steep skirts and lower lofts. This was the real advantage. Well, now they got the idea, well, let's take these mechanical filters and apply them to communications receivers. We want to have narrow bandwidth. So some of the first Collins receivers that received this, the 75A2A, which became the 75A3 and the 51J4, these were the 75A2 and the 75A3 were amateur receivers. The 51J4 was a general coverage receiver that was primarily used by the military and the government. And of course, this led to the R390 and the R390A, which was an amazing receiver, still is today. The A390A was a cost reduction version. And this is Dennis's opinion, and a lot of people hold the same opinion. It's arguably one of the best receivers ever manufactured. And it evolved out of that 51J series. The last ones, believe it or not, were made in 1984 by Fowler Industries. And I have a bunch of them in my collection. And that happens to be one right there, which was in new old stock condition when I received it, which is pretty amazing. It's a fabulous receiver. Anyway, I don't call this a defining moment, but it's still important. Up until this point, we never had combined receivers and transmitters. Everything was separate. We had a big transmitter and a big receiver, and they were separate units and all the control systems that went with that. During the war, being driven to making smaller units, we tended to want to put the receiver and transmitter in a single box. And if you think about a super heterodyne and the same scheme is used in a transmitter, the schemes are very similar. Why not share the components and the functions? So in amateur radio, a couple of manufacturers opted in, and this one I have to laugh. I chuckle about this. This is a little unrelated, but in the 1930s, National came up with something called a TRW, which stands for Transmitter Receiver in a Wooden Toolbox. It was based on an article in QST, but it was this SHF, super high frequency. It ran right around 50 megacycles. So what we call the 6 meter band. It was actually 5.5 meters back then, but roughly 6 meters, super high frequency. Well, in RCA came out with another 5 meter transmitter receiver, and that was in the 30s. It was all in one box, but they're actually they use the same components, but they really don't. They're completely different function. You switch power and do all kinds of things to switch between them. So they weren't what we think of as a transceiver today. But during the war, Abbott created this thing called a TR4, and it became a 2 meter radio after the war, but we called it a handy talkie. It was actually a luggable. It was a big box with batteries. And it was produced during the war for something called the War Emergency Radio Service when amateurs were off the air, but these were used by what eventually became civil defense, right? CD. They used these radios. Uh, in 1950, Hallicrafters created something called an SR-75 for a novice class license. It's a receiver with a 10-watt crystal controlled transmitter built into the same box. Well, along comes Collins in 1957, the KWM1, which is a full-blown transceiver, could be put in a car, run mobile, beautiful radios. But there were a host of others: Hallicrafters, Cosmophone, Night Kits, if you Allied Radio, Night Kits, Gonset. Many companies came up with this idea of putting receivers and transmitters in the same box. So the whole thing, we're scaling down radios. Okay, defining moment number 11, the bipolar junction transistor, the BJT, first developed at Bell Labs by these guys. And there's that is, I think, on display at the Smithsonian, if I'm not mistaken. Point contact with a germanium crystal. It was extremely fragile. That was point contact germanium transistor. But in 1950, Shockley comes up with this thing called the BJT, the bipolar junction transistor. It was not a point contact, but some of the other companies, Raytheon, you guys may have run across a CK722, which was one of the first commercial transistors that you could buy. I've got a few of them around here. I've built projects with them back in the day. Raytheon introduced that in 1953. They had a contest awarding $10,000 in prizes in their design contest. And here's some examples. $10,000 in prizes. The first place was $5,000. Gee, in 1953, that was a ton of money. What they did is they had a competition, and over on the side, over there on the right-hand side, they actually published a book. If you bought the transistor, you got the book with the winners. The winners of their contest are all listed there. And there's how they were packaged. That's a CK722 out of my collection in the cardboard package that they came in. And like it says, like $3.10. BA, you may recognize that. Bernstein Appleby, long gone. Anyway, fun stuff. Well, out of this came the first transistor radio, right? Who made the first transistor radio? Everybody thinks Sony. Yeah, it was Sony. That they came up with the first transistor radio. No, it was an American company called Regency. They created something called the TR1. In 1954, it sold for roughly $50. Again, that's a lot of money in 1954. It used 4 Texas Instrument NPN devices, and they made roughly 150,000 of these guys. But I mentioned Sony. Sony did go into mass production and made the transistor radio commonplace. So that was a big, big deal. Well, of course, transistors got into ham radio, right? So long before Yacom was around, which is who we know today as the big manufacturers of amateur radios, there were some transistor sets that were made here in this country. One was a Davco DR30. This is a really, really compact, high-performance receiver for amateur use. It used a field effect transistor for the first RF stage. They only made 600 of them. It's a very elegant package. It's really kind of cool. I'll have some pictures of that. I mentioned National HRO 500. That was all solid state. The fault of the HRO 500, it's a great receiver. It's very accurate, and it used an up-converted first IF, so it converts the frequency up instead of down. The technology is involved enough, you convert up, and all of the birdies and images and all of that are all out of band now, so you don't hear them, which is a real advantage to up conversion. So that was a big deal. It used a high stability phase lock loop oscillator for its local oscillator. So this was a good receiver, but they all had fault, and I'll mention that. Hammerlin HQ215, I've got one of those in my collection. It's not that great a receiver, but it really suffered from performance issues. It had some problems. All these receivers, except for the Davco, used germanium transistors. And the germanium transistors really had some physical issues. They had reliability issues. Let's put it that way. So there are the three: the Davco, the Hammerland, and the National HRO 500, and their respective dates. And, pardon me. Those are 500 is like when it works, it's a great receiver. When it doesn't work, it's a pain in the neck to get it to work. So let's talk about some early solid state attempts. Well, let's just go replace all the tubes with transistors. That's a great idea. We're going to make it smaller, less power, less heat. Well, it doesn't really work well. It limited the dynamic range. Tubes have really good dynamic range in their designs. So the next step was to do a hybrid where we combine tubes and transistors in one box. Lower power consumption, terrible strong signal performance. And that's the problem with the transistors at this point. Everybody forgot about Lamb and his 30s. How are we doing for time? Are we still good?
Maybe 15 more minutes.
Okay. We'll run through this. Okay, so defining moment number 12, digital communications age. Now, this is an interesting one. It officially started in 1948. Some of you may be familiar with Claude Shannon,
Yeah.
with Bell Labs, Claude Shannon. Everything that we use today, these guys, our cell phones, are based on what this guy did in 1948. He created something called a mathematical theory of communications. It's the founding work of what we call information theory. Information theory is what makes this cell phone work. And he based that on the work of two other guys, Hartley and Nyquist. But this leads to digital communication systems. That's what it leads to. So in 1948, telephone, cell phones, computers, radio, all these things have gone digital. Unfortunately, that article, Mathematical Theory of Communications, was published in the Tech Journal at the same time that the transistor was published. And who got the attention? The transistor. It was years before folks really caught on to this whole idea of information theory. But the transistor just overshadowed everything. It's unfortunate, but it was a big deal. That is a big deal. Claude Shannon is really a big deal in communications. So what came out of digital communications is digital signal processing. How about the first application of digital signal processing was done by Collins with the HF 2050. This was a specialized receiver built for the Canadian Air Force by Collins Radio. And the final IF, the last IF, all the filtering, so that what we use mechanical filters, we're using DSP now, and the demodulator are all done digitally, all in digital signal processing. So this was really a big step. And this is an incredibly good performing receiver, all things considered, from 1984. Well, what does all this lead to? Defining moment number 13, the integrated circuit. Yeah, good old Jack Kilby at Texas Instruments. 1958, he built the first manufactured or fabricated, I guess that's really the word I want, the first working IC. All the components are on a single semiconductor body. Small scale integration is born. Well, the oranges go back before this, but this is everything on a single semiconductor. They were doing things with multiple devices in a single package. This was not uncommon back in the 40s. TI made something called micromodules. Kilby himself had put single components on ceramic wafers to make them more compact. And that's a pretty common technique. And they could be integrated into what was called a compact grid. Well, Kilby got the Nobel Prize in Physics in 2000 for his creation, that first working IC. Well, a little more on the IC. There were problems with it. That first IC was on a germanium substrate. It was difficult to isolate the components. Well, Noyce, Fairchild Semiconductor, if you're familiar with Robert Noyce, he solved that problem. He used silicon instead of germanium. And he used a PN junction, basically a diode junction for isolation. And this leads that chain of small scale integration to medium scale to large scale to very large scale to ultra large scale integration, where we go from that very, very first IC up there at the top to this thing down here, which is some microprocessor, probably like a Pentium or something along those lines. But that's the road. Proliferation of digital logic. It's in everything. Digital applications, frequency synthesizers. No more PTOs. We use synthesizers now. No more variable frequency oscillators. Synthesizers. We can allow digitally create the frequency. We can store the frequency in a memory. We can have direct frequency input from a keyboard. Wonderful. Who was the first radio with a direct frequency input? Kenwood TR-2400 back in 1979. I'm pretty sure that's the very first one. I had one of those. I've still got it. It doesn't work. Bummer. The display is shot. But that was the first you could actually enter the frequency with a keyboard. Digital signal processing. Well, DSPs became denser integration, higher clock rates, more functions could be added, more functions in the IF, audio filtering using DSP. Yaesu comes to mind with that. The Mark V has audio DSP. Well, what comes next is another big improvement, which is spread spectrum. This was patented in 1942 by George Antheil and Hetty Markey. Now, you know who Hetty Markey was. Antheil was a composer. She was an actress. But Hedy Lamarr, you've probably heard of that. That Hedy Lamarr actually created. She and George Antheil created spread spectrum. They're the ones that came up with the idea using piano rolls to control musical instruments. They noted that torpedoes at the time that were radio controlled were very easy to jam. Well, let's use a piano roll to change frequency. So we have this mechanical system that changes the frequency around and makes it harder to jam because it's frequency hopping. So you set up identical piano roll mechanisms at the receiver and the transmitter, you synchronize them, and the signal is spread across the frequency domain through frequency hopping. That's the terminology. Believe it or not, it wasn't until 1962, 20 years later, that the Navy actually took notice of this and implemented it. It is jam resistant, jam resistance. It's not totally jam resistant, but it's much better. But now we use frequency hopping, spread spectrum techniques, and again, cell phone. Claude Shannon, it's all him. Okay, number 15, maybe, software-defined radio origins. In 1965, these two guys created something called the fast Fourier transform, and this started showing up in products in the mid-70s. Things like spectrum analyzers were using fast Fourier transform. But the hardware had to catch up to it. And I played with this stuff back in the 70s, this Redicon Bucket Brigade CCD. I was playing with this, making an audio delay line using that. But they were using this CCD to do FFT and doing spectrum analysis with it. 1984, E-Systems, which is now part of Raytheon, actually RTX, Raytheon Technologies, they came up with this term software radio. It's a digital baseband receiver, and it deals with interference cancellation and demodulation, doing it digitally. 1991, the term software-defined radio came about, and this was at IEEE National Telesystems Conference. Jay Mottola, the software radio, he came up with that term of software-defined radio. Well, the beginnings of amateur SDR go back to Gerald Youngblood, and of course, if you know Gerald Youngblood, if you know anything about Flex Radio, he's the, I think he's still the president of Flex Radio. He publishes an article in QEX, a series of articles about the SDR 1000. And that is really where amateur starts in software-defined radio. This was, I think this was available as a kit from Tapper, the what is that? Tucson Amateur Packet Radio Group out of, Tucson. So just what is an SDR? We hear this stuff all the time. Well, a typical SDR, early SDR, consisted of some RF stages followed by what was called a quadrature mixer, an IQ mixer. IQ mixer, it produces two signals that are 90 degrees out of phase with each other. You take the original signal and make them 90 degrees out of phase. So you have the original signal, the I signal, the incident signal, and the quadrature signal, the 90-degree phase shifted signal. We add an A to D converter, analog to digital conversion. We do some digital signal processing. We go into a D to A converter, so we convert the digital signal back to an analog signal. We amplify it and deliver it to the user. So this is the basic, these are the basic components of an SDR. Well, we're getting there. We're almost done. The next step was to go to direct sampling. We get rid of that all the RF stages and all that. We direct sample. And the first commercial product, as far as I know, that did that was this Perseus from Micro Telecom, little Perseus receiver. And I can't remember what year this came out. It was in the 2000s. I'm not sure what year it was. It might have been around 2008, 2009. Was an incredibly performing receiver. Covers DC to 40 megahertz in one swath. So it basically samples the entire spectrum from DC to 40 megahertz. It samples that. And then you just go in and pick out what frequency you want to go listen to. It's got a wide dynamic range. There are little or no spurs or images or that sort of thing. So this was really a game changer. So I call that my defining moment number 16, direct sampling SDR. Today, we've got lots of options. We got the 8000 series from Flex Radio. I've got a 6700 sitting behind me here. I love that radio. It's got a great receiver in it. Some of you may know Apache Labs. Their radios are quite good. Elecraft, the K3, the KX3 and the K4 are direct sampling radios. Of course, ICOM's got the 7610 and the ubiquitous 7300. Everybody's got a 7300, right? Some of you probably have two of them. I've got one and a 9700 sitting up there. Those are direct sampling SDRs, wonderful radios. Yaesu's got the FTDX 101. ELAD manufactures this thing called an FDM Duo, which is kind of a thing you can experiment with. It's a dual channel direct sampling receiver that goes up into the gigahertz range. Great Scott Gadgets, this Hack RF1. If you want to play with SDRs, this is a great thing to play with. It uses GNU radio running on Linux, and really kind of a neat piece of equipment. The GNU radio is a graphical interface where you just grab modules and you set the parameters of the modules and connect them together all in software, and you make the thing work. It's really pretty cool. Red Pitaya is another one that's one for experimenters. And of course, Xiegu even has the G90 now. Well, this is our state of the art, right? In amateur, this is really where we are right now with amateur receivers. What happens from here? Where do we go from here? What's the future going to hold? Obviously, direct sampling is the thing. We're creating higher performance A to D converters. This is one step. We're getting higher sampling rates. More bits means greater dynamic range. So higher performance, of course, that means more cost. Portability. Yeah, we want to have a portable, high performance, direct sampling receiver that I can hold in my hand, maybe. I think that's coming. We want to capture the entire spectrum, VLF, HF, VHF, UHF in one box. I don't want to have all these separate things. I want one box to do it all. So we're going to do that. And then I can capture all that stuff and then play it back later. How cool would that be? I just capture the whole spectrum and then I can go back and look for signals. I can control it remotely, like over the internet, right? Well, we can do that now, but this is cool. So I propose this is your next receiver. This is from a company called Pervices. It's called the Cyan. This thing covers DC to 18 gigahertz in one box. It has up to a total of 16 chains of receive or transmit. Okay, 16 chains. It's 1 gigahertz bandwidth per chain, and it's upgradable to 3 gigahertz per chain. So could you manage 16 chains of 3 gigahertz bandwidth? Holy cow. Oh my God. It's based on this part, this Intel Stratix 10 FPGA system on a chip. This thing does 10 teraflops of single precision DSP. 10 teraflops. Oh my God. I can't even conceive of that. I can't comprehend that number. Well, you might ask, if you have to ask. Well, if you have to ask, you can't afford it, right? fully fully populated, $280,350. That's off of their website. That's the fully populated version of the Cyan. So I doubt that very many amateurs could afford that, but governments could. I could see the FCC using these for intercept receivers. It's a pretty incredible piece of equipment. But think about it. This is this is actually a couple of years old now. This kind of technology is going to percolate down into consumer products. It's going to happen. So we're going to see stuff like this before too long. We're already seeing some pretty amazing technology in amateur radio. Anyway, that should be my last slide, and I can give you the screen back. And there's my cursor. I was looking for that flashing cursor, cursing flasher, or whatever it is. There it is. Okay, I can get rid of that. All right. Well, I'm happy to entertain any comments or questions that you may have.
Oh, okay. You can hear you just fine. Go ahead.
Can you hear me all right?
Yeah.
Or should I move up?
No, I can hear you.
You can?
Yes, I just turned up the volume here.
I'm Betsy AJ6AF.
Okay.
My grandfather was in World War I in the Army Corps of Engineers. Somebody told me that they were the guys that went in and laid the lines. Were
Yeah,
some
they
of the
did.
earlier radios and things you were showing probably what he was putting up?
Well, a lot of the early radios, I don't really have anything that was used during World War I. They actually put, believe it or not, they put spark transmitters and receivers in aircraft during World War I. And the
He was working in France.
in France, So he might have been at the signal. He could have been involved with the Signal Corps laboratory in Paris, in France.
Yeah, I've got one report. I forget what part of France he was in, but he was talking
That's
about
cool. That is really cool. If you look at something, and I want to say it was called a BC-1, Bravo Charlie 1, was the Signal Corps' first airborne radio set. I'm pretty sure that's the one. And of course, these things are super rare. I'd love to have one, but they just don't appear very often. But BC-1 is a transmitter receiver spark rig. Well, it's BC-14. No, BC wireless transmitter number 1 from 1918. That was it. And it's a little compact spark transmitter that they put in an airplane with a battery, and they can radio down, use that for reconnaissance and radio information back to their headquarters with a spark rig on CW. So it's pretty cool little piece of equipment. Those are
And then my
Yeah.
And then my uncle was in World War II on a destroyer escort in the South Pacific. He did radar, but someone I was in contact with from the ship was a radio man. And he sent me his story about his growing up and then getting into World War II. I'll have to look back at that because about being the radio man. So
radio man on the ship. That's cool.
Yeah, Setterstrom. And then one of our members just stepped out of the room, but he's a centenarian.
Yes.
2 months ago, we just celebrated his 100th birthday, and his son-in-law just stepped out with him, but it was the most they'd heard him speak. He went on for about half an hour or so talking about his ham radio experience from when he was a boy.
I heard all about that. He worked for Collins Radio, worked for Art Collins. That's all really cool stuff.
Yeah, because there's one of the other members that attended that same birthday party, and one of the other ones on Zoom. the three of us attended the birthday party and he talked. It was mainly about his ham radio experience and all.
Yeah. Yeah. We want to do an interview with him for the Collins Collectors Association magazine. I've been talking to our editor, and Brian sent me the information, and so we're going to be getting in touch with his daughter to
Oh, good.
do it. We want to do an interview and get his story and publish it in our magazine.
Oh, it was really interesting.
That's cool.
And his daughter and son-in-law were both completely surprised that he was talking so much, but he just went on about his history. It was really interesting.
That's so cool. I would have loved to have been there for that. That would have been really something to hear. That's awesome. But yeah, wow. Knowing someone who knew Art Collins, that's quite a thing. Wow.
Well, thank you, Brian, for getting that information to the speaker here.
We have another question over here.
Hey, Dennis, what do you, is, free DV gonna be a thing?
What was that again? I'm sorry.
Is free DV gonna be a thing? You think that's gonna
Well,
work?
Oh yeah, that's there. It seems to be there's a lot of activity going on with digital voice communications in amateur radio. So that's one of them. There's a couple of other ones that I can't think off the top of my head. I'm part of this thing called Rat Pack.
Yeah,
I don't know if you're familiar. If you're familiar with Rat Pack,
yeah, I'm on your channel, yeah.
okay, we've done a couple of presentations on Rat Pack on digital voice, and FreeDV was one of the ones we did. I'm trying to think of I can't think of it off the top of my head. Certainly, that's another future path. From my perspective, I'm not interested in that stuff. I don't want to just hear a bunch of bits for voice. I want to talk to somebody analog. I'm an analog guy, but the digital, there's a huge advantages to that. Look at FT8. Look at the advantages of FT8. I mean, that's amazing. And again, that all goes back to Claude Shannon back in the 40s. That's why we have all that stuff, the work that he did back in the day.
Single side on the FT8 of the 50s, right?
Yeah, well,
That's what everybody loved to hate.
yeah, the thing that everybody loves to hate. But that's where it all started. If Claude hadn't done it, somebody else probably would have. But that's really the origins of the things that we take for granted today. It's used everywhere. It's used in radio astronomy. You think about it. FT8, the whole basis of FT8 and some of the other FL Digi, these all use that technology, the based on information theory and the signal processing. That's how they do what they do. CW Skimmer, there's another one that uses the same technology. So it's out there.
If you ever want to read a really good book, his biography is called A Man at Play.
No,
Yeah.
Man.
A Man at Play.
and who was that? Who was that of?
That's Claude Shannon's biography.
Oh, Claude Shannon. Yes.
Yeah.
Uh-huh.
It's
Yes,
really-
yes.
He was beyond genius.
Yeah, he was. It's one of those guys that they just locked up in his office and let him play.
Yeah, that's what they did.
Uh-huh. Uh-huh. Absolutely.
Now, you said that you have a magazine out there?
Oh, which?
Because you said that you wanted to put this gentleman into your magazine, is that?
Yeah, we have I'm with what's called the Collins Collectors Association. We're an international organization of people like me that like to collect Collins radio equipment. And I'm a board member of the CCA. I'm also the secretary. And Brian mentioned that to us a while back on one of our nets. And I got to talking to him and then talking to our editor of the magazine. The magazine's called Signal. And it's a membership, like QST. If you belong to the CCA, you get the Signal magazine. I talked to our editor, Scott, and he's like, "Oh yeah, this would be great." So we're going to do it. We can get a hold of
My
it.
next question is,
Yes.
it was a wonderful presentation. I would like to know more history about the ham radio.
Bring John back.
John.
John, come here.
Hey,
Wait.
hey,
All right.
Dennis.
Dennis, come
Here,
here.
come up here.
John, come up here.
Is there a book about the history of the ham radio?
Come on over here in front of Don.
There's actually some recordings actually on Rat Pack about amateur radio history. Yes.
You're fine.
Okay.
Oh, wait, he's gonna move the radio.
We're talking.
Okay,
Ah.
here he is. John, whoa. Speak to the camera.
Hello.
Hello, John.
You're famous.
Yes, you are
You knew
from
his
Collins
mom.
Radio.
I was
I'm,
an engineer at Collins Radio for 5 years.
that's awesome. That's awesome. We want to interview you for our Collins Collectors Association, of which I'm a board member, Collins, the CCA. We want to do an interview with you for our magazine, The Signal, which of course Collins published a magazine called The Signal back in the day. We've carried that name forward and publish The Signal today. But that would be really, really cool if we can do that. We'd love to be able to do that. And congratulations on your birthday. That is amazing.
I'm his son-in-law. How did we set that up?
I've got your, is it your daughter? Brian gave me your daughter's contact information, so we'll get in touch with you through her
Okay,
if that works.
that'd be all right.
Yeah, on the Collins S line
Yeah.
was introduced in 1958 at the ARL National Convention in Washington, D.C. I was the presenter that made that presentation.
That's fantastic.
Wow.
Yeah. And then one of my favorite radios of all time, the Collins S line. I've got a number of them here that I use. But the 75S1 and the 32S1, right?
Yep,
Yeah.
Tell him your original call signs.
my original call sign, W8, dogs, cats, and fish.
And then, oh, you got the XE. I know when at your party, you talked about you kept the XE or something.
Well, my California call was WA6HXE. And I kept the XE and got a K7 from Utah.
Okay. Cool.
Now, is this XE that he's talking about, the one that you were talking about earlier, that much earlier in the presentation? Would that X be?
Oh, well, that was back in the day. That was an experimental license. So that
Okay.
started with an X. The X denoted those were experimental licenses back in like the 20s and 30s and what have you. When they started assigning the prefix as well, the identifier, country identifier. So yeah, things like Armstrong's, his very first his FM experimental license was that W2X something or other. I can't remember now off the top of my head. I don't remember it, but you saw that, yeah. But yeah, that's cool. That is so cool. You know, we'll definitely be in touch. Most certainly.
Anybody else with any questions or?
All right.
And
Well,
thank you for your contributions at Collins Radio. We do appreciate that very much. Did you know Gene Senti? Did you know Gene Senti at Collins?
Gene Senti at Collins?
Gene Senti.
Gene Senti at Collins.
What?
Did you know someone named Gene Senti at Collins?
Gene Senti? I don't recall that.
Yeah, he was part of the team that developed the S line. His granddaughter lives across the street from me here in Inyokern, of all things. We thought that was pretty cool. So yeah, Gene was an interesting guy. KWM1, the little transceiver was one of his creations. The 30L1 amplifier was his thing. Gene Senti. Oh yeah. Well, great. I love it.
Well, Dennis, I want to thank you for the presentation. That was outstanding.
Well, it's my pleasure, and thank you. Yeah.
You know, we've got all these years of experience of all these hams, and you know, you ask, oh, when did you get your license? Oh, I got my license back in the 50s or whatever. And
I wish.
you've completely ruined my my punchline that I always say, oh, they had radios back then.
Oh, yeah.
Now it's like 1800s or something. Now I gotta wait for somebody to say I got my license in 1700.
Well, you got a kid with it. We got a couple of guys on one of our nets that we like to kid about them that they worked with Marconi.
Yeah.
You know?
Yeah, I use it all the time. I'm an air traffic controller, so sometimes we
Yeah.
talk about, stuff in the war. I was like, we had planes back then? Like,
Yeah, right.
so,
That's
I don't
cool what
do
you
that
do.
anymore.
Thank you for what you do, by the way. Thank you for your service.
I was amazed when I became an air traffic controller. I was a ham, and it had expired, and I've got a whole story about that. But basically, I did not know after my initial in the military, my initial air traffic control training, I had no idea that the frequencies that I was talking to aircraft on, VHF and UHF frequencies, were AM.
Oh, yeah.
When I bought my first mobile rig, a little Kenwood TM241, it was VHF only, and I tuned up our local, the air traffic control tower and the radar where I worked, and I couldn't understand them because I was like, what?
FM.
Why can't I understand this?
That's
And
an
I was
receiver.
friends with some of our electronics technician guys that maintain our radios and stuff, and they're like, yeah, it's because FM. You're not going to be able to hear them. And I was flabbergasted. I was like, what? Why are we? This is like 1991. Why are we using AM? What the hell?
Well, why don't they? You know why they don't use FM?
Yeah.
Strongest signal captures the receiver, and you can't hear the other signal. With AM, you can tell that there's two signals or multiple signals there. So that's the advantage of AM.
Yeah, and as a user, as an air traffic controller, I can tell you that sounds good in theory, but when they both talk, you can't understand.
Well, you can't understand it, but you can tell that they're there.
Strongest signal always wins, and it's like it doesn't matter if it's AM or FM or whatever.
But even on AM, you can tell there's another signal there. You'll hear the heterodyne, or you'll hear that there is another signal, even if it's interfering with it.
Yeah.
The FM, you don't have that luxury generally. So that's why they've stayed with AM. I'm surprised they haven't gone to single sideband, though. They do for long haul. HF communications is all on single sideband.
Yeah.
Thanks to LeMay and Art Collins.
Yeah, Oceanic Flow, they all do.
Yep.
it.
Mhm. Yep. That's a fun thing to monitor too. If you have a shortwave receiver to listen to the long haul communications between the not just the air traffic control, but the companies on their private channels on single sideband. It's kind of cool. That's good stuff. All right. Well,
hey, thanks again. I think we're going to wrap up our meeting here.
Thank you.
well, my pleasure. Thank you for inviting me. I've really enjoyed this, and hopefully we'll get down and visit you all sometime in the future. We'll visit you in person. I would love to be down there. We've been to a couple of your meetings.
I know a handful of our members have been up to your place to see your little museum there, so I'm hoping to be able to get up there and do that if that's okay.
You're always welcome. You're always welcome here.
Thank
We
you,
like
Dennis.
What's that, Brian?
From Yuma.
Yeah. Hey, Brian, have fun at Yuma. Don't buy everything.
We're trying to.
Okay. You'll see all my friends out there.
I'm gonna stop the recording, and you're welcome to hang out while we finish our meeting.
Well, we're gonna shut down here. We're gonna shut down and head back to the